Hi, everybody. This is the Physics of Bitcoin show. It's our episode number 16. I cannot believe it that we have already 16 episodes discussing the physics of Bitcoin. I am here with my co-host, Stephen Perrenot. And so I want to tell you a little bit about the show because this is what we do every single time, because it's, maybe people are confused about this idea that there is physics in Bitcoin. Our approach is, both of us have a PhD in physics, in particular, actually astrophysics. And we have a very interesting career where we change discipline and we apply physics to these different disciplines. And we have both an interest in Bitcoin, and we want to study and understand Bitcoin using the tool that we learned as a physicist and that we applied in our work. We think that Bitcoin is a perfect candidate for this because it has a lot of regularity, it has a lot of property. It's not just a financial asset, but is also a commodity. It is backed by real physics, that is the physics of electricity, and energy consumption. So there is a material aspect to the system, but also the interactions between Bitcoiners form a network. Network theory is actually something the physicists study. Even human network, social network. There are famous physicists like Barabasi, for example, is a leader in the field that study this type of interaction, because physics is not just about studying the natural world, but also, we are part of a natural world. So when you have complex interactions and agents, it can be also understood as a physical system. So there is an interest in physics in studying economics, in studying, different kind of sociological problems, the economy of cities, for example. It's if you think of it, physics is only restricted to study, planets or thermodynamics and things like that. It's not true. Physics is expanding its area of interest, and so this is what we are interested, and we are sharing these insights with you. So most of the time, our presentation are a little bit more technical than what you will find, but that is our niche. That is our particular angle that we are trying to present here. Stephen, do you want to add anything to this?
Yes. Physics is, in a sense, universal. One could say it's physics all the way down. If you know that particular joke about, turtles being the foundation for how the Earth rests. But, physics starts with particle physics. It moves up into plasma physics, atomic physics, and onto molecular physics. And once you have that, you're getting into chemistry. So you've got inorganic and then organic chemistry, and then you're getting into biology, and eventually you're at anthropology and psychology and social behavior. So all of these things are emergent. They're layers on top of each other.
Exactly. Because for example, if there is an entire branch that is called biophysics, because there are a lot of things that you can study through the lenses of physics in biology, without talking about chemistry, that is a branch of physics in a sense, and then biophysics, but ecosystems are made by biological entities, and people have used different type of equations that are very physical equations, like a prey-predator type of, like dynamical system can be applied to biology. And then, people are nothing else than biological entities, and we interact with each other, so we can study society interactions and human interactions and productions of goods, or like through economics, or maybe organizations of large structures that, as Stephen has pointed out, are emergent properties of our activity, like cities, for example. And cities follow power laws, not by chance. So, there is no restrictions when there is like, there is no things that physics cannot study or understand, because the tools are universal. So
there's a lot of restriction. We're all completely constrained by the laws of physics.
Exactly.
We all have to live with gravity and the laws of electromagnetism every day. And, sometimes we take those for granted, but they're always there in the background.
Yeah.
And we cannot violate those laws. And those are the same laws that have been true since the very first second of the universe's existence, 13.8 billion years ago.
Fraction of a second, right? As far as we know. Like how it is 10 to the minus 41 seconds or something like that.
Well, yes. I mean, back until grand unified theory scale,
exactly,
10 to the 16th GeV, which we don't observe, but we do observe all the way back to the first second through the cosmic neutrino background, which imprints itself on the cosmic microwave background.
Yeah.
So we have observables all the way back to the first second.
Exactly. And the approach of physics, I like this word observable, right? Because that is the key. We always go back to, okay, what we can observe, right? What are the parameters we observe? How they are related to each other? That is how physicists think about the work. So it's more like a framework. It's a particular approach that it applies to almost anything. Anyway, so Stephen has a specific agenda for today because we go from the universal to the particular, and if you want to show your agenda.
Yes, and I'll talk about energy and power today, but in a somewhat different context, in the context of the bubbles, and I'll define what I mean for energy and power in that context. It's not the same as the 19 gigawatts of energy that's fueling the Bitcoin network. I don't know why this share thing. There we go.
Yeah.
All right. How's that?
Perfect. All right.
Okay. So it is the 16th show, and Bubble Power is my title. And of course, the bubbles are contained within the right-hand side of this curve, which is the distribution of all of the residuals. That's the log 10 of the residuals. So if it says 0.5, that's a factor of 3. If it says 1.0, that's a factor of 10. And you can see it's also offset from the mean. So when you're in the core power law, you're somewhat below the mean of all the residuals because it is so lopsided. And we have shown elsewhere in other shows that you can approximate this with 2 Gaussians as a sort of bimodal. But here's the agenda. First, I want to revisit some things about how both return and volatility clearly fall with time. And that's a model-free statement, but it's completely supportive of power law behavior. And then we'll look at power law core transition bubble zones, which we've talked quite a lot about, and just review that. And then I want to get on to how the residuals can be fit as a function of Bitcoin's age. And you can fit them basically with a reciprocal function, which is a 1/t kind of power law, the most simple kind of power law, first power. And then I'll talk about the energy in the major bubbles, the 4 main bubbles, and the average power in each of those. And if we take just those largest bubbles, we find that those also can be fit with a reciprocal function. The fit to energy doesn't work as well as the fit to the average power, which it fits really well, but I'll show you both. A quick analogy with fluid turbulence, and then a quick derivation as to why the average power in a bubble under power law behavior for Bitcoin price would be expected to decline as roughly a reciprocal function with Bitcoin age. And then I'll close with implications for a 2025 bubble if we actually get one going here. Okay, so first the return and volatility. This just shows for each epoch, where each epoch is up until the halving, the first, second, third, fourth halving, and the monthly averages. And the orange curve is the average monthly return for that 48-month epoch, which is 48 block months in this case. And you can see it falls quite sharply. It falls by more than a factor of 4 over a 12-year span, as you went from the, the centroid of the first epoch to that of the fourth epoch. The blue line is the standard deviation of monthly returns, and that fell by over a factor of 3. Both of those look like reciprocal curves. And in fact, if you had exponential behavior, that's the same as constant compound annual growth rate, and those curves would be expected to be flat. Certainly the orange curve would be expected to be flat, and it's very clearly not flat. This is the kind of behavior you expect with the power law. Here's the probability distribution for the residuals shown in a little more detail. And one sees clear separation into 3 zones, the major zones being the core power law behavior, which is blue shaded here, and then the long flat tail, which is due to the bubbles. And then intermediate, we have a transition zone, which is shown in a yellow orangish color. And that also has a flat tail shoulder on it. But the bubble has a very long tail, but can be roughly approximated with a Gaussian as well. All right, this is plotting the standard deviations with the rolling average. And the blue line is the 52-week rolling standard deviation. That's 1 year. And the 208-week or 4 years is shown in the red dashed line. And we do see this kind of fall steadily on average. It's more obvious in the 208-week case. And the left-hand side of the slide, that chart is for all of the residuals. On the right-hand side, we only include the core power law residuals, which are below the 0.4 level when you do a quantile regression.
And the Stephen, is 2 things. First of all, there is like a little column on the right where it shows like title, body. Can you close maybe that so it becomes a little bit bigger, your slides?
Oh, I'm not seeing that on my screen.
Strange. And on which slides are you right now? Because I think we were for
I'm on the 4th slide.
Because for some time we only saw the first slide. For some
I'm going to start over.
Okay.
Huh. Well, I've got a thing that's...
And it looks like a little bit opaque. I don't know why. It's different.
Yeah, no, there's something weird there. Let's see. Let me try. And then it wasn't allowing me to click on the menu even.
Maybe you want to restart it?
Huh. Switch to the slideshow. I'm getting this menu item that I can't click on. It's strange. Check my internet connection. Try one more time. Window. Huh. It puts up a little menu item, and then when I go to click on that to show, nothing happens.
I see.
Can you disable and then re-enable my sharing? Let's see if that works.
I did. You're sharing. Okay. What do you mean? Because usually what happens, the little slides appear and then I enable. I just did.
I've got something hung on my system with the sharing window.
I mean, we could see them. It's just they look a little bit kind of like a foggy.
Right.
And then
I noticed that.
Yeah, and when you were describing the slides, we didn't see 2 or 3. Only...
Okay, I have to force quit my Keynote and then reopen that.
Okay.
And so let me do that. I think it was a keynote problem.
All right. Apology, everybody. We have some technical problems.
Okay, now let's try again. Strange. It's when I go to click the share button here, it's not responsive. Let's see if I do the entire screen. It's as if I can. How about now?
Okay, perfect.
Okay, great. It wouldn't allow me to share a window properly, but the full screen. All right.
Okay.
Okay, so we have two graphs here. The one on the left is
maybe if you want to restart and not telling everything, but at least showing the graphs, because I don't think we had. Well, yeah, we didn't see this beautiful graph.
Did you see this one?
Go to the first one, and then I will tell you what I was able to see.
Here's the agenda, and then this one.
Yeah, we didn't see anything, so we didn't see the agenda.
All
nothing.
Right. We'll go back to this. So this shows for each of the 4 epochs leading up to the first through fourth halvings, so up until a year ago, what the average return was within the epoch. And we can see in the orange line that dropped from 30% in the first epoch down to around 7% in the epoch that finished a year ago with the fourth halving. And it looks roughly like a reciprocal. And the standard deviation dropped dramatically as well, from 80% down to about 25%. So the return dropped by a factor of 4 over a 12-year period, right? As you went from roughly the center of the first to the center of the fourth. This standard deviation fell a factor of over 3. This sort of behavior where both look like reciprocal curves is expected with the power law. And it's not what you see with exponential growth that's typical in stock markets and other financial assets, where you would see flat lines, particularly for the orange line of the average return. That's roughly constant compound annual growth. This next slide shows the probability distribution of the 3 zones that we've looked at in some of our prior analyses. And what we find is that, and you can do a hidden Markov analysis and it gives you a similar result, but these are simply divided into the lowest 40% of the residuals around a quantile regression. And that's the core power law zone. Then the middle 20% is a transition zone shown in yellow. And the bubble zone is the highest 40% of the residuals. And we see a very distinct Gaussian style core in blue. We see a bit of a fat tail in the transition zone with the right shoulder. And then the bubble zone is very wide, has a very long tail. And the core part of it looks somewhat Gaussian. And of course, the range is quite large here because it's a factor of 10. As you go from 0 to 1.0, that's a linear factor of 10. All right, this is another way of looking at the standard deviations as rolling averages. And the blue line is a 52-week rolling standard deviation. The red line is a 200-week rolling standard deviation. And they're unnormalized. So if you're thinking in terms of a 1-year time frame, you expect to see more total absolute volatility over 4 years than you see over 1. And you have to divide the upper curve by square root of 4 to normalize it. And you see if you do that, it would move down to roughly the same pace that the 52-week curve is. The right-hand plot has the same things, but only for the power law core, below the 0.4 quantile. And here, the first thing you see is that the standard deviations are lower by a factor of 4 to 5. It's very much lower. So things are not bouncing around nearly as much in the core. And it's also pretty flat once you get to around 2016 for the 1 year, and certainly by about 2020 for the 4 year, which took time to get enough statistics to actually plot. Now we can fit then for the full set we can fit the residuals to a simple reciprocal. And the equation is shown on the left-hand plot up at the top. It's A divided by T plus B, where T is the age of Bitcoin in years. A and B are the two parameters that you're optimizing for. And you find good fits, to the eye, good fits in both cases. It's more clear for the 208-week rolling standard deviation. That has a pretty high R squared of 0.8. It's more noisy for the one year with an R squared of around 0.5. Now, if you try the same thing on the core, they're not good fits. The R squareds are very close to 0. Basically, it's pretty flat after you get past, say, year 4. There's a big gap in a couple of places because that's where the bubbles are. So, you don't see much between 4 and 6 and between early 8 and just before 10, because that's where the big bubbles are.
Yeah, that is consistent with having a power law with Gaussian distribution, right?
Right. Now, again, you have to normalize the upper curve, divide by the square root of 4, because it's 4 times as long, 4 times as much data. And the slopes agree. After normalizing, the slopes are about 0.9. That's this A parameter in both cases. But there's the B parameter is the asymptote. And so it tells you in the long term, what's it headed towards. And you find out it's headed towards, something like 13 or 14% annualized. You get slightly different B values, but they're pretty consistent with each other. So the annualized long-term, taking the higher R squared curve is maybe 15%, which is, pretty reasonable when you think about in terms of financial assets like stocks. So the message there is that volatility is clearly coming down, and it's coming down in a reciprocal 1/time fashion, and maybe headed towards some sort of, more stable value in the long term. Now, this is what I'm calling bubble energy. This is showing the percentage deviations over the full time span, but only for the bubbles. That is, it's only measuring the part that's shaded in is only the bubbles. So if it's more than 0.6 quantile, then it's shaded this soft red, pink, whatever that color is. And you'll see there are 4 large bubbles, the ones that are well known in 2011, 2013 peak, 2017 peak, end of 2017, 2021. There are also 2 very small bubbles. And, I didn't make any selection. I let the algorithm do that. But there's this small bubble in the 2019 timeframe. That was the pre-COVID little incident before COVID hit. And then 2024, at the very end of the year, we got a little bubble before we dropped back in. So our bubble kind of faked us out at the end of 2024, as we all know. Okay. And you can look at those also in terms of, instead of percentage deviation from that 0.6 quantile, you can look at them in terms of, log 10 of residuals. And this is what it looks like. Doesn't look quite as sharp, in log space. But you see the same 4 large and 2 small bubbles. Okay, so the question I asked then is, how much energy is in these bubbles? So this tabulates the 6. We have the start date and the end date. That's when it first crosses the 0.6 line and when it then crosses back down. We have the duration. We have the peak week, the week of the peak. We have how many weeks from the start to the peak. And then we have what I define as the energy, which is the percent, I use the percent deviation, times the number of weeks. It's the integral under the curve, if you will, or really just the sum of, for each week, what was the percent deviation. You can then calculate an average power where you divide that energy term by the duration in weeks. And then we show the age of Bitcoin at the peak. And then how much of the energy total is on the rise portion compared to the fall portion. So what do we observe here? First, the largest ones have durations of 69 to 93 weeks. There's one small one, the 2011 at 25. The other two are negligible, and we're not going to include in the rest of the analysis. The weeks to peak ran typically 16 to 38 weeks, and the energy was around 6,000 to 16,000 in these units. It was 8,000 for that 2011 bubble in these units of percentage deviation times number of weeks. And the average power ranged from 84% to 312%. And you can already see that the average power is greater earlier on than it is later on. So it looks like there's some dependency on age, and we'll show that. And then the rise percent is, less than 50%. So you're spending 23 to 35, 36% in the rise portion. The sixth one kind of doesn't matter because it wasn't really a real one. Okay, now if we just look at energy and try to fit a reciprocal, and we use all four, it fails. We get an R squared of 0.02. It just was not as energetic as the second bubble, and it makes the whole thing look flat. But if we look at just the three bubbles, then there is a good reciprocal fit. It's 0.96. Now, I should caution that if you only have 3 data points, it's not that hard to get a high R squared when you have 2 parameters. But still, it's still a high R squared. And you can see that this histogram, it matches pretty well the data. And if you do a power law fit, it has a slope of -1. This reciprocal, sorry, minus 1.05. This reciprocal fit is a slope of -1. So a power law fit validates the reciprocal idea. Now, power gives us a better fit, and we can include the first 2011 bubble in the analysis as well and still get good fits. So I have here a smaller table that has the 4 big peaks, their duration, the average power, 1 over the age, which is what we end up fitting as the linear parameter, and then the reciprocal fit. And you can see there's good agreement. So the average power was 312%, the fit was 313, 172%, 168% was the fit, 98% average power, 103% was the fit. So pretty close fit. The intercept 0.25, which tells you the kind of tapering off for the long run. R squared extremely high, over 99%. There's a good chi-squared, and the t-test on the slope is 1/12 of 1%, which is very good. And on the intercept, it was less than 5%, which is suggestive of a good fit. So the large histogram shows the reciprocal fit in the blue line, and then the actual data in the green bars. And then the inset shows a power law fit, and that had a power law index of -0.83. So one cannot distinguish between those two, but the fact that the power law is close to a -1 is, they're confirming each other, both with 99% R squared. Now there's an analog from fluid turbulence. Turbulence models, we mentioned a few weeks ago, the Kolmogorov, and that has an index of 5/3, and these are inverse. So it's like 1 over t to the k, where k is some index between typically 1 and 2. Kolmogorov is 5/3. There's another one that's well known that's 10/7. But typically simulations may show from 1 to 2, depending on the conditions in the fluid turbulence. Often a form that's a reciprocal form is used. So it has a constant a, and then you divide by the time, but there's an offset time, t0. And you raise it to some power n, and if n is 1, this is in the denominator, so it's a positive number if t plus t0 is in the denominator, then it's reduced to a reciprocal, but it's just that the second parameter is put together with the time rather than separated out. So a little bit different form, and I show the fit to this kind of form of the reciprocal to the same 4 data points, and that's the red dashed line, and you can see it's a very good fit. And then I show again the power law fit here. And they're both quite good. They're both 0.99. The one that's of the form a over t plus t0 raised to the power of 1 turns out to be 10.32 over t plus 0.95. That's in years. And the 10.32 is a ratio. So it's basically saying 1,000% roughly over t plus 1. So it's a one-year offset.
Let me understand this in terms of the significance, both for the normal turbulence application and then the interpretation for what concerns Bitcoin. So in general, this tells us if you have some turbulent flow, as time passes by, it becomes more stable, right? Or the turbulence dissipates. Is this the interpretation of this formula?
This thing is
for a normal, yeah.
Well, this thing is introduced to avoid an infinity at 0, right?
Yeah.
At 0 time. And they call it virtual time. And so they also refer to it as kind of a startup time for it to kind of get going before it hits this reciprocal power law.
If this was, let's say, a gas or whatever, what the age will mean in this case? What will be the physical interpretation?
The age would be whatever, the temporal units are.
Since
the
turbulence are created.
Well, it would be more like, the natural time scale for that flow that you're studying, right?
Okay.
So it would be some relatively modest percentage of the overall time duration that you're studying for the flow.
Okay. And the fact that it decays, what is the interpretation of that? That the turbulence dissipates?
This is turbulent cascading down, and it's decay of the energy in the turbulence.
Right. Okay. So basically, there is some turbulent flow, and as time passes by, it dissipates. Right? Is that the right interpretation? Okay.
Right. This is dissipation of the power in the Bitcoin bubbles in analogy to dissipation of the energy in turbulent flows as they restore to laminar behavior.
Exactly. So you have this bubble that is formed, and then it decays naturally, right? And it takes a certain time to decay, and this is what we are showing here.
And as it does that, large bubbles move down in scale to smaller bubbles, right?
Right. Yeah, it's a beautiful analogy. I love it. And you can see it fits very well, right? The physics. This is why physics works, because these models apply to so many things, and it makes sense, right? Because of course, in the beginning, you will have a more turbulent flow. It's easy to move around, etc. And as the system ages, there are dissipation forces, that makes the bubble decay. That it really makes sense. It's a beautiful analogy. Yeah. Okay, I think you understand it.
Great. Right. And the value of n equal to 1, for the analogy, can correspond to isotropic turbulence and free decay, as they call it. Okay, so it's going as the reciprocal of the age. Why would we expect that? Diminishing volatility is expected as Bitcoin matures, the price movements become less volatile and reduce average power. The market has increasing adoption and liquidity, and so that makes it more efficient, reduces some of the speculation, the extremes of speculation. The growth dynamics, inherently follow a power law decay, because you've got scaling and power laws of the underlying asset, both the address counts and the hashing rates and difficulty, as well as the price. The broader acceptance and increasing institutional involvement helps stabilize the market. And the, Sailor comes in and buys, right? Regularly. And the fractal and self-similar dynamics, inherent scaling of speculative bubbles, can naturally lead to inverse relationship. So there's somewhat analogous to a damped harmonic oscillator or decaying oscillations in, some sort of physical system, and energy dissipation. And we've talked about how there's self-similar and fractal-like bubble dynamics in Bitcoin's price before, when we looked at things like the Hurst exponent. And we looked at also the scaling and structural analysis. Okay, now let me actually derive it from the power law And the next slide, why average power should be reciprocal of age. The price goes as T to the K. The price is a power law. K is about 5.8. If we take dP versus, derivative of price with respect to time and divide it by price to get the percentage change, it's K times T to the K minus 1 divided by T to the K. The constant drops out, and it's K over T. So the percentage price growth is the first derivative, which is K over T. To first order, you get compounding, when you look at a year, but it's instantaneously, it's K over T, which right now for us, K 5.8 divided by 16.2. So you can see why it's a large number. The bubble power, I hypothesize, is proportional to the capital ingest, and therefore proportional to K over T. Why? Because a percentage price move is equal to a market multiple times the capital ingest divided by the number of coins. And M is the market multiple, which in the power law core tends to be about 2.5. It can become quite a bit larger during bubbles. But overall, that's something like a 2.5 for the long-term trend. Now, the number of coins is fixed. To the extent that the market multiple is fixed for the core, but varies especially in the bubbles, the capital ingest is a percentage of market cap, which is a percentage of the price move, and that's proportional to K over T. So the bubble power should be proportional to the capital ingest, which is K over T. And that's a 1 over T reciprocal law behavior.
Fantastic. I love it because now everything is connected, right? So we say many times how the bubbles are not a different phenomena. It's just another expression of the dynamics, that many times you have this analogy between the laminar flow, that is the power law, and then turbulence, right? But the two are connected, and now you found a connection. That is amazing and beautiful. Thank you. They are connected with each other.
Yeah, of course. Good. Okay, so with all of that, we can create a scenario for this bubble, assuming it happens, it gets started. And let's assume that it starts late April. And let's assume that it has an average duration, which would be 80 weeks for the big three. And then that, it spends about 3/8 of that time heading towards the peak, a little less actually, then it's closer to a third. Then the weeks to the peak would be about 25 weeks. So if it starts in late April, then it would peak in around Halloween. And you can fit to the power and say, okay, how much would be the average power in this bubble, in the 2025 bubble? And it would be ominously 66.6%. And that's down from 8. Yes.
Okay, talking about prophecies and numerology.
Well, I didn't do anything. That just happened. That's what fell out. Obviously, the numbers will be different if the bubble starts later and if the duration is different, etc. But these are kind of averages. And the last bubble was 84%. So it's a drop. It's like 20% smaller relatively, but it's not a huge drop.
Yeah.
And now you can then further use that for a price projection. And you can say, based on the reciprocal curve, the standard deviation should be 0.12. And then if you go to 2 sigma, right, in the bubble, then it's 10 to the 0.24, a z-score of 2, and that's a factor of 1.7. You then have to ask, what would the power law trend be by Halloween? And it would be, based on the quantile regression, 100,000 multiplied by 1.74, you end up with 176,000 or so.
Yeah.
Could go higher than 2 sigma, but that's the 2 sigma.
I got something very similar where I fitted an exponential instead of 1 over t, but probably we are very close, because of they are kind of similar decays. And when I fit an exponential through the peaks, I didn't do as good job of you like yours, right, where you calculate the entire energy and so on, just the peak. But I like the energy, the power idea. I was getting 80% deviation from the power law, but you
Okay.
got 74%. It's basically 74%. We got very close results, very similar results. That is interesting. Yeah.
Yeah.
Two different methods. Yeah.
Okay. That's what I have. Thank you.
I love it. Very interesting. Yeah. So it makes a lot of sense. Okay. So I will discuss instead slightly different topic. Let me show my slides. Okay, here, share. I don't know. I always try to do the same thing. I watch videos and etc. One day you have to show me. Maybe we do a call and you show me all the steps.
Did you hit slideshow yet?
Not yet, but
Okay.
now I will. Is anything different? No.
No.
No. Okay. Well, I'm trying. I don't know what I have to do different, but one thing I can do, I can try to minimize this. Maybe this makes it a little bit bigger. Okay, is this slightly better?
There's a slideshow icon at the bottom.
Okay, let me try
at the very bottom right.
Yeah.
It's the last icon, I think.
I just clicked it. Nothing?
No.
Yeah, it has to be some kind of setting problem with my PowerPoint, maybe. Okay. Anyway, so we are trying to avoid polemical stuff in this show. We want to focus on the science, etc. But I had this short exchange with Corey, so we'll try to avoid any personal commentary, etc. It's not about people; it's about ideas. But I do understand Corey feeling because he was actually one of the critics of Plan B, and he did a very good job in bringing up very strong criticism. But I am even a stronger critic of Plan B. I know it looked like I came after Plan B. I didn't. I actually came up with the power law ideas related to Bitcoin in 2012, even before anybody knew about Plan B. And my discovery of a power law in time, that is an evolution over my early ideas of a power law, came around 2018, and everything that Plan B did was in 2019. In fact, from what I understand, he was influenced by the power law that I discovered, because for many reasons. We are not going there. Maybe one day we will talk about Plan B in the show and, the S2F model, the history of it, etc. But right now, that is not the point. So I understand his criticism, but one of the things I think it's not correct when people approach the power law is that they are not aware of all the work we have done. Maybe they just heard something, they have some misconception. So I want to address this misconception. So, he's saying that the power law is not backed by science. We are, all our work is the opposite of that. We are trying to show that there is science behind. And then is talking about, it's this usual criticism. It's just it's just a regression, first of all, like that, it's a dismissive of anything. There are tons and tons of paper where, in particular, observational papers, where the main result is a regression of data. Now, sometimes it goes, people abuse, people abuse all kinds of things. Like, for example, in the sociological sciences, there is a name for that. It's called p-hacking, where people try many, many parameters to find some kind of correlation between two things. They change slightly how they plot things, or the parameter they use, or which kind of outliers they exclude, and then finally they get barely some kind of correlation. I worked in neuroscience, and I was so surprised how so many results that are published they have very low correlations. Sometimes even like 0.5 or 6. But a physicist will not even consider it a correlation at all. We are used to things much higher than that. But with Bitcoin, we know how high these correlations are in the 90% type of correlation. That is and we are not talking about a couple of points. We are talking about thousands of points. That is really unique. It's something that you don't find in financial data usually. So it will be a mistake to dismiss it because it's simply a correlated, some kind of regression. Now, there are some limitations, and maybe in the next shows we will talk about in looking at logs. That is correct, because it's one of the things that happen when you take logs, you minimize the fluctuations, right? And so one criticism could be, well, you're making everything kind of flat. But we know that this is not the case for Bitcoin. First of all, because this problem happens when your range is very small. Somebody posted something a few days ago about stocks looking under certain conditions as power law. That happens if your range is very small. But with Bitcoin, we know that at least one of the scales, the price scales, change by many order of magnitude. In fact, if you look at the entire data set, it's about, if you include also the early transactions, is about 8 order of magnitude. That is incredible. It's going like from an invisible grain of sand, microscopic grain of sand, all the way to Mount Everest. That is the type of range we are discussing. And if you look at the available data, since the exchanges are open, that is 6 order of magnitude. So it's an amazing, incredible range. Now, the time is only, if you start from the from the creation of Bitcoin, it's about 5,000 days. So it's about 3 order of magnitudes. But if you plot, for example, price versus addresses or price versus hash rates, both axes have an enormous range of magnitudes. And the power laws are very clear. So that is one of the criteria where that these possible limitations of looking at power laws do not apply. And so, all these things, eventually we will publish papers. And, this is one of the things we want to do with Stephen. We will have books written about, we need probably one single website where all these results are listed and discussed. We are working on that. It's a lot of work, for 2 people, but eventually we want to do all these, for the community and, the world, because the world needs to understand all these beautiful regularities in Bitcoin. So these are criticisms that are valid, but we address them. If we didn't ever address them, will be will be okay to have these criticisms. But we did. It's just that many people are not aware of all this. So let me go a little bit more in the details. The other criticism that he raised, and many people have, is this idea that just a second, give me a chance. I'm looking at the right slides. These ones. Is that he says physics training has led many otherwise intelligent people to fall signal. Well, it's not true, because in the same time, one of the most successful funds in existence is the Medallion Fund, that was led by a mathematician / physicist, because he also contribute to physics with his mathematical models. And the entire company, the people who work in the company by choice, were physicists, astronomers, mathematicians. In fact, some people joke that it was the largest physics department in the world. And this is, one of the beautiful things about the market is that if you're right, then you will be successful. It's not bullshitting around. You cannot bullshit around with these kind of things. And they show that it uses, of course, like always, everything, if you push it too much, or you bring it to the extreme, it can lead to wrong results, right? But in general, people know this is why there are quants, right? You you know, in that movie, The Big Short, right? And at a certain point, we talk about the quant. This is what quants are physicists, mathematicians, they work for Wall Street. And there are a lot of them, and there is a reason. These are not people that have a very little criteria for bullshit, because, you know, it's a lot of money is at stake, and they know that it works. You know, physics works for understanding the market. So it's not a valid criticism. So anyway, what about, these are some of my replies that I kind of already mentioned. You know, people, so it's something that we use all the time in physics. So he was saying, oh, it's an exaggeration. There are these are other things he was saying, that there are a lot of power laws in nature, etc. I don't know where he took that. Of course, like again, sometimes we get too enthusiastic. I show that shirt, right? That is kind of a internal joke for physicists. I went to a physics conference, and all what I got was a lousy power law, right? This shirt that sometimes I show in my slides. I didn't make the shirt. It's an internal physics joke, because it's true. Like many times, you know, if you rely, oh, it's all power laws, then, you know, it becomes a little bit ridiculous. But it's a true thing. You can make a list of all the major physics laws, and a lot of them are power laws. We didn't make it up. It's the truth. And they come up in many systems, particularly complex systems, phase transitions, criticality systems. They come up naturally. And this is because of a mechanism. But the mechanism involves are where, instead of adding things, right? Like, for example, you get a Gaussian when you add different probability. If you multiply, if a process is a multiplicative process, so non-linear, you will get power laws. That it's what you can show mathematically. And this is why they are so ubiquitous. And network theory, it's ruled by power law. So if you starting with an idea that Bitcoin is actually a network, and there are many reasons, theoretical reasons why it is, and people mention it all the time, right? It's one of these things that is kind of intuitive, but then you can demonstrate that actually it behaves like a network. It has all these network properties. Power laws will come up naturally. So Bitcoin is much more. So this idea, this is why I called it a theory. And I don't know if Stephen agrees, but it's a theory because we have a more comprehensive way of understanding Bitcoin. It's a framework that allows us to interpret a lot of the things that we observe in Bitcoin. So you start with a theory, start with a hypothesis. You're going beyond just an observation that there is a pattern. You're trying to explain it. You're saying, okay, it's a network. I'm expecting all this power law behavior. And then the beauty of Bitcoin, it has these on-chain parameters. And then you start to see that all the major on-chain parameters are power law. There is a power law in addresses versus time. There is a power law in hash rate versus time. The two are related. And you can show the power law we observe in price and time. It's the consequence of two other power law. The power law between price and addresses, that is also called the Metcalfe law, that is a theoretical result that was proposed and it has never been demonstrated directly. A little bit where it works, there is some paper that show, for example, that the sales of advertisement in many social platforms. I have to talk about this in my X, about this paper that I read, but it looks like almost all the social network platform, not much the money that is not much of a this was not much of a stock itself, but the sales that these different platforms get from selling advertisement follow power law of a number of people involved in the network. There are beautiful power law that appear everywhere, in Facebook included, for example. So the Metcalfe law works in this case, that the real value, the production value of these platforms is related through a power law close to Metcalfe, that is the square of number of users in platforms like social media platform like Facebook. And it's just one example. There are several. Bitcoin works in the same way. The number of addresses, that is kind of a proxy for the number of users, gives you the price if you square the number of addresses. That is a power law. So it's a theory that tells us why we should expect these power laws, and then we observe them when we see them in many different places in the blockchain. So it goes much beyond being just a regression curve. And this particular result, for example, that Bitcoin follows a power law between, it has a power law between price and addresses. I mentioned it. Unfortunately, I didn't write a paper for whatever reason. I had a full-time job. I was busy with that. I was doing neuroscience, and Bitcoin was more like a hobby than my full-time job. It is now. I'm a full time Bitcoin researcher now. I didn't write the paper, but I have social media that are time-stamped, where I say there is a Metcalfe law between, and this was all the way in 2012. It was a Reddit post. I know it sounds ridiculous, but it's still something that can be proven with a timestamp. That I have a graph, I show a graph, I shared it on Reddit, and I discovered it before anybody else. Well, I cannot demand, I cannot, assume that that is fair, that Sornet, it is one of the most famous financial physicists in the world, knows about my Reddit post. So usually when scholars do research about previous publications, they don't go and look in Reddit, right? So I don't use it against them, but it's great actually that he confirmed the same result. He has here a nice, beautiful graph of a relationship between, this is a older paper, so they don't have recent results, but they go all the way to 2018, when I mentioned this law in 2012 in my Reddit post. So this relationship, right, between the price and active users, addresses, right? It's a power law. In fact, you can see here, they show the power law. This is the power law, the formula itself, right? They mention there is a power law between these two things. This is the Metcalfe law, where in this case, this is the log of a price equal, like it's a straight line. This is the equation of a straight line. So this is y, this is your x, this log of u, that is the users, right? There is a constant. If you remember from high school, this is the typical equation of a straight line, right? This ln, that means log, natural log. You can take also the log of 10. These are the users. This is your x. This is the slope of a curve, beta, and this is a constant. Beta, the slope, is actually the power. So if you write this as a power, it will be the price equal some constant to the user to the beta, where beta, it's a number very close to 2. I think when they measure it, see, they try to measure it at different places, but because the bubble kind of confuse a little bit this relationship, but it's kind of close to 2. It's 1.74, something like that. So there is already a peer review paper where 50% of our theory that there are these two things interacting. Well, it's we have also hash rate and everything, but my main thesis is the power law that we observe. It's the interaction between two power laws, the growth of the addresses, that is also power law. I didn't know at that time, when I talk about the Metcalfe law, that also the addresses were growing as a power law. I didn't think about it because, see, that is the other silly things. People say, oh, you just found a regression. Okay, why nobody else did it before? These things are not natural to think immediately there is such a thing. The natural thing was, I thought, Stephen, can you turn off your microphone if you don't mind? There is some background noise. Just mute yourself, if you don't mind. So, I didn't know that there was a a power law regression, a power law growth of addresses versus time. I thought it was more like an S curve of adoption, and it turned out it was not true. It's actually a power law, and that is also a very important contribution, because there are other papers, and we can discuss next time, that show that social networks, both the nodes and the link, grow as power laws. And that is another incredible confirmation that, yes, it's another evidence that Bitcoin is a network, because both its nodes and links grow like other social network. And there are papers that are dedicated for that. In fact, they are trying to dismiss this idea that these social networks grow as S-curve, because everybody, Fidelity, etc., they always mention this S-curve. There is no S-curve in Bitcoin. There is a power law of growth of the addresses that is scale invariant, and social networks do the same. So I did all that work. I use the same equations. We can discuss that in the next episode. That one of these papers that I mentioned uses. It's a agnostic equation, because it parameterizes all the possible equations that you could get. You get Weibull curve, you get an exponential, etc. And then you want to find the correct parameters that fit the data that you observe. And if you when you get the parameter from the fitting, it turns out to be a power law. And so Bitcoin nodes that are basically the addresses. So the nodes in the systems are, the computers, for example, in this case, the users are the nodes, and the connections between them, because of this Metcalfe law, is the price. And so both the price and the connections grow as power law. That is what you're expecting from social networks. So all these are incredible contributions that show that it's a scientific discovery that we have done. It is backed by science, because we are creating the science. Yes, the science is already there. Like, for example, the science that shows that social networks follow power laws, and we are showing that Bitcoin is similar. So that is where the science comes from. And there are already peer-reviewed papers that discuss these power laws, at least one of them, in like a very nice journal, like Royal Society journal. They publish this particular paper. So it's not true that there is no science behind. So there is a lot of science, and our intention is eventually to create an institute, a scientific institute, to study Bitcoin. So I don't understand how advocate of Bitcoin dismiss the idea that actually Bitcoin deserves to be studied scientifically. It does, because it's a very interesting system, and there is a lot of science behind it. And then this idea that power laws are not predictable. I have mentioned this so many times. I have an entire video where I explain that. In fact, there are a few times where physicists feel quite confident that we can make prediction. And by the way, let me say this for the people that are not very familiar about science. Science is all about predictions, because in fact, in particular with physics, this is how we know that we are into something right. When our theory can predict something, right? If I understand correctly how gravity works, I should predict when I drop an object, how long it takes to arrive to the ground. My theory should be able to tell me, I solve a problem. We give this all the time to students. Calculate how much time it takes for the object to arrive to the ground. That is a prediction. When you send a satellite to the orbit and it has to arrive to a particular height, etc., all that is a prediction. You calculate how much fuel you need, how much energy you have to apply to the rocket, and it arrives exactly there to the point that you can contact a space station or something like that. When we are able to send probes to Mars within a few hundred meters from where it's supposed to land, where you want to make it land. So we are predictive. Physics is predictive. Now, the level of prediction that you have when you send a rocket is not what you are going to get when you are trying to predict a complex systems like Bitcoin. But these are predictive too. And power laws in particular, the main idea behind the predictability of power law is that this idea of scale invariance, right? And I explained many times this idea. Scale invariance means that the system at all the different scales has some characteristic that is invariant. What is invariant here? The relationship, the scale relationship between some of these parameters that you mentioned. It depends on what you're looking at, addresses, hash rate, but in particular, if we want to think about the most famous one, that is price and time, the scaling in time, and the scaling means going to different sizes, different order of magnitude. So if I go from 10 to 100 to 1,000, so the way that Bitcoin changes scales and the way, in time and in price, it's invariant. In fact, it's a straight line, and a straight line, it's an invariant thing. It's linear and it's predictable, because you know exactly, you can write an equation, right? That is what is, it's the rate between these two, it's a constant, right? The rate of change of this quantity relative one to the other, of price relative to time, it's a constant, right? In terms of scale, if you express it as a scale. And that is something that is predictive because it's a property of a system. There is a reason why Bitcoin follows a power law, because the mechanism behind how Bitcoin works, the way that it grows, the way that the price reacts to this growth, are inherent property of a system. So you are expecting that unless there is some huge change in the system that can happen, we call them phase transitions, but we don't see anything right now that it's a phase transition. The ETFs are not a phase transition. Government buying Bitcoin is not a phase transition. In fact, actually, you can use the scaling property to kind of make a prediction of when that probably is going to happen. You can say, I think it's going to happen when this order of magnitude in the market cap, etc., is reached. What actually Stephen was talking about, that even the decay of a bubble is proportional to the market cap, right? It has to do with the market cap and how much flow comes into Bitcoin. All these things are actually predictable things. And the power law, it's the tool that we use. And look at this, there is an entire paper that actually discusses the predictive power of power laws. So how can you prove somebody wrong when there is an entire scientific paper, he says it's not backed by science here, showing that actually power laws are predictable. So there are two times when we feel very confident. I was saying this in physics, to make prediction. One is periodicity. So if you observe a periodicity in a system and the periodicity has been observed for a long time, the likelihood that the periodicity continues is pretty high. So if this is how, for example, we can tell that tomorrow the sun is going up, because we have observed it many, many times, and we think that the periodicity will continue to exist. And the other one is when you have some scaling property like that. That is very predictive, and we do it all the time. Engineers use it every time they try to scale up. They make model of a system. In fact, they sometimes to save money, they make a little model of an airplane that has the same characteristic, the same shape, etc. They test it in a relatively small wind tunnel, because it's very expensive to make a full scale wind tunnel. And then they know how to scale, what are the scaling principle to go from a small model to a huge big airplane. Same thing when they build a building. They know which kind of structural property a building has, and they can scale up without making new calculations or new models, by simply applying wherever they know it works for a certain size building. If they double, triple the size of a building, they know how to do that. That is something that is used all the time. The scaling property is one of the most predictable things that it's just somebody that doesn't know the field, is not familiar with power law, they don't use it all the time, will say something like that. There is no predictive power. There is a lot of predictive power in power laws. So that is the other point that I wanted to make. And here another research paper, right? So researchers find a better power law that predicts earthquakes, blah, blah. So we know, for example, even in financial, there is this other thing, right? It is called the Sornet actually is an author of it. They are called log periodic power laws. They are predictive of crashes, for example. And in fact, the price approximates a power law. And if that happens, that you can stand that power law, and it's predictive of when the crashes is going to happen. But there are other things that scientists discovered that are, again, scaling property. This article is a very nice article that talk about all this scaling property that you observe from blood vessel, earthquakes, etc. And you can make predictions. You can make predictions about the health of a subject by looking at the scaling property of his vessels. That there is some kind of problem, there is and you can actually tell this person is going to have an heart attack within a certain amount of time because we see some problem in his vessels, etc. All based on power laws. So it's a very predictive tool. And again, people are saying these things because we are not aware of the science. And we show that, this scaling property applied to Bitcoin, because see, here is what I plotted. It is very, this graph, that seems very random. Basically, what I did, I took the ratio between the price at any given day. So imagine every day, right? So you have a price P2 and price P1. So P2 is the price today, P1 is the price yesterday. So I took the ratio. So I see this is what it says in the y-axis, log of returns, right? Returns in this case is the ratio between the price today versus the price yesterday. And this, you get this, right? It is kind of crazy. Now, you know what you get if you express it in days from Genesis block? You get in average, right? Because if you take the ratio between the log of a price over the log of a time, in this case, it will be T2 over T1, right? In fact, this is very similar to the 1 over T law that Stephen was talking about, because basically this will be the age of Bitcoin today versus the age of Bitcoin yesterday. So it will be time T1 plus, if yesterday was the time T1, right? So let's say 5,321 days, right? So this was the age of Bitcoin yesterday, let's say. Well, today will be plus 1, right? So the ratio between 5,321 over 5,320 will be T1 plus 1 over T1, right? And that is kind of like 1 over T type of relationship. Now, if you take the log of this quantity, and then you take the log of the ratio of the price, and you take the ratio log of the prices, right, over the log of the times, that is a constant. And it should be, if the power law is correct, close to the power law constant we see, right, the slope. And this is the distribution of these guys. This is the distribution of these slopes. It's exactly the power law. It's the slope of the power law, 5.89. And so basically, we can show beyond see, this is going beyond being just a regression, because we are showing that is a deep statistical property. So statistic is involved, but it's not just the only tool to understand Bitcoin. It's a property of Bitcoin, because in average, even every single line, it's almost, imagine every single day there is like a mini power law. These mini power laws in average are the general power law we observe. And so it's something deeper. It's not just some kind of stretching the diagram, finding a line where there is not a line. It's something deeper that you can arrive to without doing the regression at all. You can show that Bitcoin follows a power law just by measuring all these little changes over time. There is no regression here. And you can show this is what happens, right? These are the log returns. These are log returns average over 1 year. It follows this pattern that is correlated with the bubble. See, this is where you have a peak of the log returns. This is where you have a minimum. It's actually a very nice way to pick up the tops and the bottoms. And this is where your average slope is. It's in the middle. And I did other tests where, you show these relationship, right? So this is the ratio of a price, taking the logs. This is the ratio of a time, right? The age of a system today versus the age of a system yesterday. I did it not just today, yesterday, I did a random times, right? So I pick up 2 random times, day 5,200 versus day 300, right? And then I calculate the change in price between these 2 days. So I take the logs of this ratio of the age of a system, age 1, 2 versus age 1, take the prices, you do it over and over again, you get a power law. And in fact, it's the same power law, the slope that we observe with an R square of 0.95. And you see, sure, there is some variability, some fuzziness because there is noise in the system, but in general, it follows a power law. No regression here. This is no regression. This is a scaling test. In fact, actually, it's one of these fundamental tests that it's basically a group theory property of scaling variance systems. So this is very sensitive test that shows that Bitcoin is a power law, and you are doing this test without using regression. So it's another way of showing that Bitcoin is a power law without invoking regression. So it's not just regression at all. And here is very interesting because see, I did it theoretically, right? Here I took a power law, just an equation that, see, this is a theoretical power law in my graph. Here is kind of small, but in this graph I have linear time and the log of price. So the power law will look like that, right? This is very familiar. It's that rainbow type of curve, right? That we are so familiar when you take only the log of Bitcoin, the price, and linear time, right? This is why not many people recognize this curve being a power law, because you look at this graph, you immediately don't know that is a power law. You will have to take the log of a price and the log of time to see a straight line. And then if you know about power law, you say, oh, wow, that is a power law. Many people didn't realize. Now, the straight line here, the black one, it's an exponential, because if you take the log of the price and the log of days, you get a straight line. It's an exponential. So I took a theoretical exponential, I took a theoretical power law, and I added some noise, some fake noise, and I did this test that I just explained, right? You take 2 random times, you take the log of a ratio, and then you take the change in the value of the price, the ratio of a change in price. And the theory tells us we should get this red line. Now, if you take the exponential, you should get this kind of funny ribbon or whatever, right? Okay, I did it with Bitcoin, the real value of Bitcoin. I get this. Look, it's exactly what the theory says a power law should look like under this test, the scaling variant test. And when I took gold and the SP500, the SP500 is blue and gold is black. Both of them are exponentials. They look exactly like the theory says. No regression. And I show you that are power laws. That Bitcoin is a power law and anything else is not. So I don't know if this is now science. Absolutely science. In fact, this is a publishable paper if you show this particular test. That is a very interesting way of showing how you differentiate the behavior of Bitcoin versus the behavior of other assets. So yeah, there is science behind all this. Very interesting science. Any comments, Stephen?
I'm never intimidated by MBAs.
Yes, exactly. So, win is not an argument from authority, but, I think people should start to understand that physics is very relevant for Bitcoin. And, we do have experience. We know what we are talking about. And of course, we will never say, hey, guys, you have to believe us because we are scientists and we are PhD and we have used the power laws all our lives. I am completely aware of all these issues. There are many times where I don't sleep at night thinking about, am I right about this scaling variance thing, etc. And then, how you resolve this, anxious feelings by doing the calculations and testing it and retesting it and retesting again and coming up with all sorts of things to show, yes, it's indeed a power law. And we know, we have shown it in so many times. And, if I do this with what we call the core, it will look like a straight line. In fact, I'm going to do it. I'm going to take out most of this fuzziness is due to the bubble. If you take out the bubble, that thing will look like a straight line, almost perfect straight line. And remember what they did. They pick up choice. Understand the craziness of this test, right? You pick two random points. You look at the price. You take the ratio of the price. You take the log of that, and you divide it by the log of the age of a system. It should give you a power law. And it doesn't work with any other asset, which only works with Bitcoin. So I don't know what else you can show. There are other things that we can come up with, but it's a very powerful test. It is not a regression, right? Because a regression can have some problems, etc. This doesn't have anything to do with regression. But people are not aware of these studies, and they say this thing. They should stop because we went beyond. The regression was just a starting point. It's not at all the final point. Anyway, let's look at some of the questions. Okay. I don't know about this person. In general, as a physicist, I don't like woo-woo. I don't like it. And I think people can have personal opinions, and among scientists there are many atheists, there are people of faith, etc. But what is in the end the thing that kind of is common for all of us is we agree that when we try to convince each other, we are not going to say, hey, my faith is better than you, and I'm going to bash you on the head because you don't believe in my faith. We are going to have a rational discussions. We are going to give evidence. We are going to follow the scientific method. This is how we made progress, and people from different faiths, different religions, different worldview can actually agree on what is real and what is not, because we have this very precise step-by-step procedure and a method of doing experiments and verify. And before that, it was all opinion. When you study philosophy, there was, I was very surprised when I took philosophy class in my high school, and they were telling me, there was this Greek philosopher that thought the universe was made of water. Water was the most fundamental element. And there was this other guy that thought it was fire. And then this other guy said, no, there are 4 elements plus ether. And who was right? Well, eventually science say none of them is right. There are not such things like with elements. For elements, there are, the 100 element, 100 whatever there are, 120, how many there are elements, and all these things that we discover with science. We have a method, right? And this is why I don't like woo-hoo. And in particular with Bitcoin, because if you start to say, I arrived to this price because I got a dream, well, it's not reproducible, right? It's not something that you can explain to people how you arrive to that conclusion, what are the pitfalls of your thinking, what are the range of applicability. We always tell you, if we look at these and then we see this pattern, this is the level of confidence that we have. We always tell you what are the limit of what we are doing, and that is how you do science. So in general, I don't like people that believe in woo-hoo if that woo-hoo comes in their science. If they have it as their own private worldview, everybody's free to believe what they want, So that is my position about that. Do you want to comment anything else about woo-hoo in
Well, woo-hoo generally is not falsifiable. So
right.
to be science, it needs to be falsifiable, and there need to be repeatable experiments or repeated observations. In the case of astronomy and astrophysics, it's repeated observations. So
yeah, so falsifiable for the people that maybe are not super familiar with this term means that you have to point out what needs to be shown for the your claims to be not true, right? So for example, with the power law, it's very easy. If a price starts to go for quite a bit of time, right, away from the range where we can give it a certain range, okay, it needs to deviate by such a percentage, not to be a power law. It needs to stay away from power law behavior more than 6 months or 1 year, right? We know, for example, the bubbles usually the last 2 years. In these 2 years, we deviate pretty much. Now, if a bubble lasted 10 years, we could not say, oh, this is just a deviation, right? It will be like the Black Knight saying, oh, this is just a flesh wound, when a harm left, right? So we are very strict on that. Yes, we saw that the price goes back to the power law after 2 years. So that's kind of what we are expecting. If it goes beyond that, then it's not a power law anymore. So the power law theory, it's falsifiable. And usually these woo-woo kind of things are not, because there is no way to show that God is not talking to you, but they usually don't work either, right? So they could get it right once, but they cannot do it over and over again. While science, it's repeatable. Yeah, I'm working on the book. I already started, and at a certain point, I would like Stephen to be my co-author, but it's something that I need to work on and be serious about it. I need to spend less time on X and more on writing papers and books. Okay, then we have this one. Okay. Well, we are all, I'll just come here for a reminder that I'm very average human. We are all average in something. Einstein, you always say, I'm not a very intelligent man, I'm very passionate man. That is one of the things that always apply to myself. My intensity in our approach science is all based on passion, so this is why sometimes I'm obsessive, but it's part of, I don't think you can get a PhD in anything if you are not obsessive. It comes with the job. Anyway, the noise of a network. I don't know what this comment means.
Yeah, I'll comment. A lot of interesting things here, Josh, and thoughts. And I think to some degree, you're onto something kind of interesting overall. I don't know if it's the noise or, the energy that's powering the network, right? So it's, why is the price the square root of the hash rate? Or conversely, why is the hash rate gone as the square of the price, roughly, right? A power law that's roughly double. It's something we observe. I don't know, it's something like the 11th power, right? That the hash rate is something like the 11th power of time. It may have flattened a bit in the last few years.
Yeah.
It was certainly easier to grow hash rate earlier on because you were transitioning from CPUs to GPUs, then to ASICs, and you were in the early stages of ASICs development, so it may be a little harder, and so there may be some flattening toward the 8th or 9th power, and I worry slightly about that, because if hash rate is flattening, does that mean that the price power law would flatten too? But we have not seen the price power law flatten. But it's certainly a reflection of energy invested in the network. I think it's market cap. Look, it's the quantum here is the electron. It's electrical energy. It's electrons that are being converted into highly secured bits, secured by the hash rate. And those are kind of high value bits. They're not random bits, right? Because they have so much cryptographic lock-in, both through the hashing process and the fact that these blocks are chained to each other. And then you have to invoke the Poisson law derivation that's in the white paper, right? That says the further back you go in the chain, the exponentially harder it gets to break. So that's all the investment, how that translates into something, I'm not quite sure. It's some form of entropy, right? Because it's encoded information. So I think Shannon entropy comes into play here. It's not something that I don't know if you look at that.
Yeah.
Giovanni.
What happened? We lost it for a second. We kind of, it was like a glitch.
Yeah,
now
no,
it's good.
It's entropy that's being encoded.
Yeah. Now I had an argument why and it could be a wrong argument, and it doesn't have to be an alternative argument. It's kind of related now. But there is a proportionality between price and hash rate. Is kind of obvious, right? If a price goes up, more miners want to join in, so this will increase the hash rate. If you include the the difficulty adjustment, because it's part of a loop, right? You will need to adjust for two things, because basically what happens, right, as more miners come in, because they are attracted by a higher price, the difficulty adjustment will go up, and that will make the hash rate to increase. So that is part of it, right? Has to be like that. But why the square? Because the difficulty adjustment has to adjust two things: the proportionality of miners that come in relatively to the price, but then also the price itself, because the reward needs to be more or less constant, right? That is the entire idea. So now you have to adjust for two things that are kind of independent, and so their product will be relevant, not their sum. So you have to, and the product, it's price times price, because the number of miners will be proportional to the price, but also the reward now it's higher. So for the same time, for the same amount of energy that they spent before, now they get more rewards in USD because the price is higher. So the difficulty adjustment needs to kind of be proportional to the square of price. It's kind of a order of magnitude argument, right? But it seems right? What do you think about that?
Yeah, it's not quite clear that it has to be the square, right? But both of those products, to some power, relatively high power.
Yeah.
The other thing that's going on is that the understanding that this is a brutally competitive business, because the lifetime of your capital, it decays very rapidly. You may have, we now have in the US, the top dozen publicly traded mining companies, and I track this, I issue a report every 6 months, have about 25% of the hash rate just in those 12 companies. And, they struggle to make money, even though they're the most efficient, and they've gone to the most efficient sources of electricity, the cheapest electricity, whether it's in West Texas with wind and solar power, and whether they're getting some reduction because they agree to contracts where they shut in their power and so forth under peak load conditions. But even they are finding that they have to diversify their revenue sources. So many of them are moving towards offering AI hosting as well. And that will make them more efficient, and it will take down some of the noise for them. And so that allows them to also continue to invest. It's fascinating, the economics of it. I don't think it's that investable compared to just Bitcoin itself, because it is such a harsh business.
Yeah,
but I buy your general argument that it's a product of both of those factors.
Yeah.
And as price goes up, more people want to contribute, and they need faster and faster machines.
Right.
And ultimately, the ASICs get fabbed at TMSC and at Samsung, so that they definitely make some money.
Yeah. Now, I love this question because it's something that I always say. So, what is the Fermat principle? It's basically the path of least resistance, right? That is a very general principle that we observe in nature, right? When water goes down from a mountain, it's going to find the path of least resistance. It's a question of, it seems we don't know these kind of things. Why nature likes that? Why nature likes to minimize the energy in a system, right? It's one of these things that we don't understand, but it's such a universal property that we use it to solve a lot of problems. When we give you a physics problem, it could be very, very difficult to solve all the details, but you say, hey, calculate the energy at the top. I know that at the end is going to be the same, but the least resistance. So it's something that allows you actually to solve a lot of problems very quickly because you are using this minimization of energy principle. And yes, I think the power law is exactly an expression of that. Bitcoin is finding the path of least resistance to do what is supposed to do, that everybody that is a maxi agreed that is supposed to be eventually the monetary system of the world. So it has this immense task of going from basically a joke or kind of an experiment when it was created, that people were making fun of it, to be one of the greatest invention of mankind, one of the things that revolutionized our understanding of money, our understanding of finance, and more and more institutions are taken seriously. Will you ever imagine, for the people that are, you probably heard about Bitcoin, even if you didn't buy Bitcoin 10, 12 years ago, 13 years ago, and you thought it was silly, could you ever imagine the president of the United States will go to a Bitcoin conference and to have a plenary session, or that he will pass laws or make a committee, about Bitcoin? It will have sounded ridiculous, right? And it happened. And there will be a day when nations will make now they are discussing, but there will be a reserve that is equivalent or maybe even bigger than gold in Bitcoin. It will happen. All these other things happen. And how is doing this? Well, if you talk to a physicist and you ask how Bitcoin will scale to go from a few $1,000 network, or even zero when it was created, to trillions, and in fact the same size of all the wealth of the world in 10, 20 years from now, it will tell you it will be a power law. It will grow as with some scaling property like a power law. You will have said that from the start. And it is. And that is because of this conservation of energy property, this least least resistance path, etc. Yeah, the Fermat principle applies. I think it's exactly what we are observing here. It's the optimal way to do what Bitcoin needs to do. It's a power law. It's not surprising. It's exactly what you will expect.
And it's a meta network. It's a network of networks. There are at least 10 networks involved, and they are, adaptable, and there's feedback between the different networks, right? And so the whole system adapts, to least action. Yeah. You get these bubbles where people, FOMO, and you get into excited states, and maybe that's not least action, right? People are getting overexcited, but then it has to collapse back to the least action principle of the power law.
Yeah. So you see, it's really a very scientific understanding of Bitcoin. So when somebody says no backed by science, it's not correct. I understand the skepticism, but this is what we are trying to do. This is why we spend time with you. This is why we have all these ideas about writing paper, etc. It's not something that we do out of nothing. There is a lot of principle ideas that really apply to Bitcoin, because Bitcoin is this amazing system. And that is one of the things that puzzles me when people dismiss this, and they are Bitcoin believers, because you should be, if you are a Bitcoin believer, you should believe that Bitcoin follows something that goes beyond chance, that these numbers go up is not just an expression, it's actually based on real evidence and mathematics and science, So anyway, I know ideas sometimes take time to be understood and accepted, and then there'll be a day when everybody thinks that Bitcoin being a power law is just common sense. One day that will happen, but we are not there yet. This is why we need to do a lot of work still. Anyway, guys, and there is something about Shannon. And at a certain point, maybe we should going that direction. I kind of started, I think one time I did post something, I calculated the entropy of a system, but it's something that needs to be explored. This idea of Shannon entropy, so information theory, very interesting. I think it's very relevant to understand Bitcoin. But have you ever done anything with Shannon entropy and
No,
Bitcoin?
I'm not.
Yeah, it would be interesting to actually calculate it and show the different entropies for the different. So how much you will expect less entropy during the core, right? And more entropy during the bubble. So it's something that I maybe even can try next time. Actually, it's a very good, it's not that I didn't think about it. I think at a certain point I even did it. I don't know why I didn't continue in that direction, but I can revisit. Actually, thank you, Josh. Maybe that will be what I do next time. I will calculate, I will do a moving window Shannon entropy and see what happens for the different modality in Bitcoin. That will be a very interesting result. Yeah, in fact, if you guys have a suggestions of things that you think we should explore, we can. We take suggestions from the audience. Okay, thank you so much, guys. This was another very interesting episode. And we will see you next week. Bye. Bye, everybody.
Thank you all.